And our presenter is logging in, and our presenter is logging in from her institution in Georgia. So we'll be getting back to you with some more announcements in a few minutes. In the meantime, just hang on. Welcome everyone. K-12 Resources in Nanotechnology, January 31st, 2014. This webinar is brought to you by the NAC Network, established at the Penn State College of Engineering and funded in part by a grant from the National Science Foundation. We gratefully acknowledge those. This webinar is hosted by Maytech Networks at the Maricopa Community Colleges. What we want to find out today more about is nanoscale science and engineering resources for K-12. Our presenter is Joyce Allen. She's the Assistant Education Coordinator. Joyce, when we were talking the other day, you were telling me how you got into this field. We can read your bio there online, but tell us a little bit how you made the transition. I think you were a teacher originally, weren't you?
I was a teacher. I taught 30 years. But I got into nanotechnology because I actually kept hearing the word nanotechnology and figured it was something that my students probably needed to know something about, but I didn't have a clue what it was. So I actually looked for an opportunity one summer to actually learn about nanotechnology so that I could take it back to the kids. And I actually spent a summer in a clean room running thin films and characterizing them. And that's how I got involved with NNIN. I actually worked for NNIN that summer.
It's pretty interesting. I noticed on your brief bio here that you're also involved with the research experience for teachers as well as the REUs for undergraduate students. That's an interesting program, and I bet if some of the teachers on the line wanted to hear more about that, they could contact you at the end, couldn't they?
Yes, we actually have our application for having research experience for teachers at some of the NNIN sites is actually online, so teachers could actually go online and actually apply. That's actually what I did that summer. I was actually selected to be one of the RET teachers that summer.
And here you are today. Well, good.
They found out I was retiring. They actually tried to have a connection between the research world and the classroom.
Well, that's great, and in fact, I think that's a critical sort of skill that you bring here because our teachers, our faculty, we're always trying to make that connection. I'm going to go ahead on the presentation, Joyce, and I'm going to turn it over to you so you're now in control. Go ahead and tell us about your objectives for today.
Thanks, Mike. Again, welcome to all those who are participating in the webinar today. As you can see from this slide, I want to start off by talking about some reasons that we need to expose kids to K-12, the nanoscale science and engineering. I also want to talk about some big ideas in nanoscale science and how they connect to state standards. And I also want to highlight a variety of resources that we can use to teach nanoscale science in the curriculum that we already have in K-12. To help us know who's participating, I want us to begin by actually doing a couple of poll questions. And so if you'll go to the poll button that Mike showed you earlier, if you could put in what grade level you teach, A for elementary, B for middle school, C for high school, D for post-secondary. And if you do not teach, if you could go down to the chat box and actually answer whether you provide outreach to K-12.
Thanks, Joyce. I see a number of people have gotten their selections in. It's a pretty easy question since most of us know what we're doing. And also in the chat, you'll see some people giving a sense of where they are outside of that teaching realm. Now, people online, let me give you just another second to finish your polling question. You can keep chatting there. Joyce, I'm going to count down to 3, and then let's take a look at the type of people that have joined us today. So here we go. Counting down 3, 2, 1. So there it is, Joyce. I'm going to reposition this slightly. Looks like your largest category here is high school, but you've got quite a spread of participants.
And that's great because I want to try to show resources for K through 5 all the way up. So this it's great that we've got some from each of the categories with us.
I'm going to go ahead and clear this poll because I know you have another one coming right up.
Okay, so the second poll question that we would like for you to answer is, how familiar are you with resources for nanoscale science and engineering? Answer A if you're very familiar, B if you know some resources but not a lot, and C if you know nothing about resources for NSE. And again, in the chat box, if you don't mind answering, what do you hope to gain from participating in this webinar?
So everyone, please use your polling buttons up there for the ABCs. And instead of the chat window, to put in your ABCs, go up higher to the participant window, those icons. There's 4 of them lined up horizontally, and choose one of those. You know, I'll say where they're filling it out. I'm always looking for new things to change it up in my classroom, Joyce. You know, perhaps an animation, a simulation, some way of, so I don't have to talk to the students. They can stop listening to me and do something else. So that's what I'm looking for. I just thought I'd throw that in there.
And that's the great thing about having a variety of resources that you can actually pull from. So we hope when the participants get through today that they do end up with a variety of resources that they can actually go to.
Okay, I'm going to publish the results of the poll. I'm going to count down and close the poll. 3, 2, 1. I did that fast. And there's our results. Let me reposition this here right there, Joyce, so we can see what we have. Looks like we've got pretty good familiarity with NNIN. But some people who still are looking for real help here. Interesting.
And that's great. That gives us some ideas on how we can help the participants with resources. I actually want to start today talking about why we should actually expose our students to nanoscale science and engineering. And I want to start with a slide that I often use when I'm talking to teachers and also to students. This is a slide that actually provides some information from the National Science Foundation, because on the right side you'll notice that by 2018 they estimate that nanoscale science is going to be a $2 trillion industry, or 5% of our gross domestic product. And also by 2020 that we're going to need 6 million workers to manufacture nanomaterial and products. I think that helps students to actually have a feel for career potentials that are out there. And I think students need to know those types of things. Another thing that I often like to give students is information about STEM in general. So you'll notice on the left side of the slide I've given some statistics from the Labor Department. And one of those statistics is that by 2018 they estimate that we're going to have over 8.5 million U.S. STEM jobs, and that STEM jobs will grow faster than non-STEM jobs. Again, I feel like this is information that will help students know what the potential for careers are. But since the webinar is based on resources, what kind of resources can you use to kind of get this kind of information? So as I begin this slide, I want to actually talk about where these resources come from. You'll notice on every resource that I use today, somewhere on the slide I've provided the source. But what I want to point out to you is the participants don't have to write down these sources, because after this webinar is over with, you'll end up with a long list of resources, and all of these sites will actually be on there. So that's one of the things that you'll end up with. So let's talk about what you can get off of a site like this one. This is actually the usinnovation.org website. And this is a website where every state has a STEM report card. The great thing about these STEM report cards is it provides lots of information. One of the things that it actually talks about is the number of research dollars that are actually spent in the state. Another kind of interesting piece of information you can get off of this report card is it actually talks about the interest level of your high school students, the high school students in that state, as far as STEM disciplines like science and math and technology and engineering. For example, here's a statement that I got off of 2013 Georgia STEM report card. And it says that by the year 2018, we're going to need to fill an additional 211,000 STEM-related jobs. See, that's information that I think that students need so that they can plan for what they want to develop a career in. Another place that you can go to for information to support including STEM is polls that have been taken. Here's an example of a Harris poll that was taken in 2012 of U.S. adults who are over the age of 18. The interesting thing about this data table is, if you'll notice, over a third of the adults stated that they knew nothing about nanotechnology. And the interesting thing is, these possibly are the same adults who are out there buying consumer products that have nanostructures or have been developed by processes of nanotechnology. Thank you, Mike, for pointing that out. Here's another point from that same poll, and this one actually shows that older adults are much more comfortable with the risk and benefits of nanotechnology than young people are. I'm not sure why that is. But the thing that it tells me is that we've got to continue to help these young people have enough knowledge so that they can actually make some educated decisions. Another thing that happened was the National Science Foundation felt like that it was important that a discussion be held back in 2006 and 2007 about what should be the things that students should know about nanoscale science and engineering. And so NCLT and SRI actually got together groups of industry people, educators, researchers, and had some discussions about what should be the big ideas in nanoscale science and engineering. These ideas were actually put together in the book that's shown, which is The Big Ideas of Nanoscale Science and Engineering, a guidebook for secondary education. This is actually a book that's actually published by the National Science Teachers Association. The great thing about this book is it actually goes over the big ideas, but it also provides some goals that teachers can have for addressing these big ideas. It actually talks about the prerequisites that students should know to understand the big ideas. But a thing that I like in this book is it also talks about misconceptions that students often have about these big ideas. When I'm doing a workshop with teachers, I always stop before I introduce the big ideas, and I want to do the same thing today, because if you're a teacher out there, I want you to actually think about the curriculum and the science concepts that you teach when you see the big ideas. Here are the 9 big ideas of nanoscale science and engineering that came about because of the conferences that were held. Now, teachers that are looking at this slide, how is this different from the science that you already teach? And I think that's an important thing for us to understand is you're already teaching about nanostructures and processes that are influenced by nanosizes. It's just a matter of teachers recognizing when they have an opportunity to discuss the unique properties that occur because of these nanosizes. So if you look at your state standards and the categories, a lot of these categories for our state standards are the same categories as the 9 big ideas. So nanoscale science and engineering concepts are easy to integrate because they do align to the state standards that you have. I've got a couple of slides that are coming up that actually show how the big ideas align to next generation science standards. I don't want to spend a lot of time on these slides because you actually know your state standards much better than I. But I do want to show that they are incorporated into the concepts that you have in your state standards. Here's an example of K through 5, 4 big ideas and some next generation science standards that they connect to. The thing that I really want to highlight for K through 5, and I'm often asked, why do you feel that there is a need for us to do outreach to K through 5? I truly feel that K through 5 create the foundation. They form the foundation skills that these kids are going to take into middle school and high school. And so one of the examples is when you're talking about nano, and that is actually a size, they begin that journey on learning what a nano is actually in K through 5 when they start doing things like base 10 number properties. And so that's an example of how they're forming the foundations that we will eventually build on. So K through 5 I feel like has some great places that we can actually have a discussion with kids on nanoscale science. Here is 6 through 8. I took 4 big ideas and I actually related those to some of the next generation science standards that are out there. And of course, again, if you look at some of the categories to our next generation science standards, structure of matter, for example, not only is that a category for our standards, but it's also a big idea. Here's an example of 9 through 12 science standards. The first one that I listed up here is self-assembly. And I'll kind of share some of the discussion that I've gotten back with high school students on self-assembly. I have an activity that I do, and oftentimes before I do it with students, I ask them if they know of anything that self-assembles. And a high percentage of the time I get back nothing or blank looks. Even though these are the same students that have gone through biology classes and they've talked about the replication of DNA or the 2 cells coming together to form a more complex structure, or even have sat in chemistry classes and taken one reagent and put in a test tube and put another reagent in and get new products at the end. They sometimes forget that those are things that are actually out there being self-assembled by the forces that are out there. And so this is an example of 4 big ideas and how they relate to next generation science standards. As far as resources are concerned, I really want to start off by just talking about what if you want a resource that just introduces nanoscale science. In other words, you don't want it to connect to a standard or concept that you're doing in your curriculum. You just want to use it as an introduction, maybe as a research opportunity for your students, or maybe an enrichment. I want to kind of go over some resources that you can use. You'll see the topics that I kind of want to concentrate on. There are many more than this on the list that you'll end up getting at the end of the webinar. Here's an example of a lesson that you can use that just introduces nanoscale science. This is actually a lesson that uses societal and ethical issues of nanoscience to introduce students to what nanoscience is all about. This is actually a lesson that comes off of our NNIN website, and you'll notice that it actually has, and I was going to highlight, but you'll notice that it has a teacher prep guide, it actually has a student guide, and it actually has the next generation science standards that it addresses. Another great place to get some lessons that just introduce nanoscale science is actually the NISE network. This is the NISEnet.org website. This is actually a variety of lessons that you can get from there. You'll notice that they have all the teacher preps, the student sheets, any PowerPoints that go along. You'll notice that those are actually listed under resources, but they also have the evaluations that are listed under the evaluation tab. Here's an example of the problem that sometimes teachers run into with resources for nanoscale science. They find a great resource for nanoscale science. The only problem is it's much longer than they have the time to commit to that resource. For example, it may be a lesson that requires that it takes a week to do. So here is an example of a unit from NanoSense, and this is a unit that is called Size Matters Introduction to Nanoscience. This is a unit that has several lessons to it. But here's an example of how you can take a piece of that unit or that resource and actually use just the piece of it. This is actually an activity that is a size sorting activity that comes from lesson 2 in this unit. This is a unit that I don't even use the way that the lesson asks you to use it, because normally when I use this activity, I'm only with students and maybe teachers for a short period of time. But this unit actually has the students relate the size of objects to the logarithmic scale. And so it's a great activity. It has worksheets that go along with it. It even has the evaluation to go along with it. So this is an activity that I use anytime with students and at teacher workshops. Here's some examples of students who are actually doing this activity. I actually have the students line these cards up from the smallest object to the largest object. And I do that for a reason. The reason that I do that is because when you watch students do this activity, you'll notice that even though I've instructed them to line the cards up from the smallest to the largest, most of the time they will take the large objects, line those up first, and then go back to the small objects. And that creates an opportunity to actually talk to the students about why is it that they line the large objects up first. And they'll tell you, these are things that we are familiar with. And so often I tell the students, and that's exactly why sometimes you're in a class learning about things that you're not familiar with, so that you can have those as things that next time you see those objects, you'll actually know some things about them. And so we actually use that as a jumping off point of talking about the different sizes that objects are. I do this activity all the time with students, and I also do this activity a lot with teachers. Out of all of the hundreds of times that I've done this activity, I've never had a group to get all these cards lined up correctly. It's kind of surprising when you are working with students, even though you've taught them about the different structures, sometimes the size of those structures they don't really think about. For example, one of the cards is a nucleus of an atom, one of the cards is an atom, one of the cards is a molecule, and sometimes kids don't get those lined up right because they forget that if a nucleus is part of an atom, it must be smaller than an atom. And so it's sometimes you begin to see that students know a lot about structures, but sometimes size and scale is not something they're familiar with. This is another opportunity that I use to actually talk to students about understanding that that you could start grouping objects into 4 worlds of measurement. And so we talk about the macro world and the micro world and the nano world and the atomic and the molecular world. Another thing that
Joyce, can I interrupt you for just a second? It's Mike, I'm sorry. I was just amazed that in the hundreds of times you've done this, no one has actually gotten it perfectly lined up right.
Neither students nor teachers. And I do this activity at teacher workshops all the time. And I think it's the same reason. I think teachers are familiar with the objects that they are familiar with. And so sometimes objects that are on these cards that they're not exposed to a lot, they're not really sure about the size and scale of them. But it's something that I say to teachers with these cards is think about think about the things that you actually teach about all year. Can you turn those objects into size cards? For example, we've had biology teachers who have actually taken the structures that they teach about all the way from parts of cells all the way to biomes, and they've actually turned those into size sorting cards, which are cards for their own subject. And I think a lot of us have topics in our curriculum that we could actually do that with. We've also done size sorting cards. We don't use these with elementary students. I only use these with middle school and above. But we also have a set of size sorting cards that we do with elementary.
Thanks very much.
Another resource that you could actually use to just introduce your students to nanoscale science is, of course, books. In addition to the resource list that you will have with internet and multimedia resources, you'll also have a resource list of books. Here are some examples of books that are on that list. And I'll point out this first book, What's Smaller Than a Pygmy Shrew for K through 5. That is actually a book that we have actually created a set of size sorting cards for. So this is a book that is used on a lesson that's called What's the Smallest Thing That You Know. The great thing about K through 5 is it's a great opportunity to do STEM because you can do language arts and math and science and put technology in there and cover a lot of concepts. And so you'll notice that some of our elementary lessons are actually based on books. And in the middle you'll notice these are 6 through 8 books. The bottom book actually is a little book that's about viruses because, of course, viruses fall within that nano range. To the right, you have some books for 9 through 12. The first book, Nanotechnology Demystified, actually is a book that at the end of each section are questions that students can answer after each section, and also questions at the end. A great place to get books is if you don't have the money in your own science budget to get books is, of course, to go to your media center and see if your media specialist could actually have some books that she could put in a section for you. But in addition to that, if you don't have money to buy a book on nanoscale science, the book on the bottom on the right of this slide, Nanotechnology's Principles, Applications, and Implications, is a great book that is free online. It's a book that was produced by the European Commission. It is actually a book that has actually been used by many high school students in Europe. It has some great nanoscale information in it, as well as some hands-on activities that teachers could actually do with students, and it is free for you to download online. That is also on your resource list. The only problem with that is it is quite a big document, but it's well worth printing out, especially if you don't have a big for buying books. What if you want to use some type of multimedia to do an introduction? I'm going to actually introduce 4, give you some resources really quickly on this webinar for 4. And so I want to start really with that website. This is a great website. You'll notice that it actually says K through 12 resources, but it also says create an account. Teachers do have to sign up to be able to use the resources on this website. And you'll notice that when teachers go to a lot of the resources that are listed on the resource, it will ask teachers to actually sign in. And let me explain to the teachers who may not understand why. A lot of these resources are actually created by grant money, and those funding sources actually want to know who's using the material that was developed. So oftentimes these sites will ask teachers to actually sign in so that they can actually keep up with who possibly is using the materials. So this is an example of where teachers will have to sign up, but it's free to sign up. So once you sign in, get your account and click on K through 12 resources, and it will bring up a screen that looks like this. And you'll notice that there's a whole variety of types of resources that you could actually get off this site. But if you look under the introductory modules, you'll notice that there's PowerPoints there. So let's say you are a teacher out there and you actually want to do a PowerPoint introduction about nanoscale science, but you don't really have a clue what kind of information you need to provide the students about nanotechnology. There are places that already have introductory PowerPoints already produced, and here's an example of where you can find one. And once you click on that unit, this is an example of the introductory PowerPoint that you can actually download from that site. So it's a great way for you to actually do an introduction without you having to do a lot of the work getting it ready. And as far as time is concerned, I realize that teachers don't have a whole lot of time to go out there and find a lot of this information. And that's the reason resources like this are of value. What if you want to do an introduction by having your students do a type of Webquest? Here is a website here from Wisconsin that actually has several Webquests on there. This is just one of them that I've pulled to show you. This one is from Small Science Come Big Decisions. These are some websites that actually have students learn about a variety of places that nanotechnology is actually being used. And you'll notice that it has a tab that has an introduction and a task and all those types of things on it. And in fact, I don't know what I just clicked, but if you'll notice up here, there's task and choices and evaluations. But when you click on the task that actually comes up is that you are a nanotechnology researcher that works for NNI. But you've been told that your budget's going to be cut, and so you have to do a proposal. You have to present your case in front of the National Nanotechnology Budget Review Committee on why you should get some of that research money. And so the students divide up into groups, and then they pick an area of nanotechnology to actually research. And you're going to notice that there are some great categories where nanotechnology is actually impacting our lives. And when you click on these categories, it actually brings up a PowerPoint that provides lots of information to the students, but it also links out to some additional sites. The other thing that's great about this webinar is every PowerPoint, it doesn't matter what category you're in, every PowerPoint actually has guiding questions that will actually guide your students as they're developing their presentations to present before this budget committee. So it's a great way for you to actually have your students learn a lot about nanotechnology. There are some great places to get Webquest. We're actually going to have a new Webquest on our NNIM website in a few weeks. Another problem that often teachers tell me about is that as they're introducing their students to nanoscale science, their students hear about pieces of equipment that are used in the field of nanotechnology, but teachers don't have those pieces of equipment in their schools. They're not near a research university. So a great way to introduce your students to some of these pieces of equipment that are actually used is to actually use simulations. Here's an example of a simulation of an electron microscope that of course comes from discoveryeducation.com website. The great thing about this website is the students actually select a specimen, actually place it here on the platform, and the screen will actually show you what that object actually looks like when it's scanned under an electron microscope. And then what the students actually do is they actually decide what that specimen is actually showing. And so it's like a game in the sense that the students actually have an opportunity to actually see whether they can decide what that specimen is actually showing. The screen will tell them whether they're correct or not. So it's a great way to introduce students to pieces of equipment that you may not have available in the classroom. What if you wanted to use just a video to introduce your students to nanoscale science? Here's actually a set of videos. It's a video library that you can find at the NanoWorks website. And it has categories that videos have been classified under. And you'll notice there's a whole set of categories. In fact, this category, this one video that's under art, is actually showing how nanoparticles, the images of nanoparticles can actually be turned into art. And of course, some of you may notice there's one called Cool Stuff. That's actually where videos of songs that have been created for nanotechnology are actually placed. So there's some great categories for different things that can be shown to your students to introduce them to nanoscale science. So if you're looking for a video, here's an example of a place that has a whole library of videos that you can click out to. Another good way to just introduce your students to nanoscale science is by a demo. The problem with demos is you have to figure out who your audience is. Is this somebody that you're going to have for a short period of time? Is it somebody that you can have a longer discussion with? And here's some pictures kind of showing what I'm talking about. To the upper left here, This is actually a outreach opportunity that we did at the TELUS Science Museum, and this is actually we were actually doing a discussion with the students that you see standing there about hydrophobic and hydrophilic materials, and then they would move down to the table and actually make a hydrophobic and a hydrophilic spoon, and at the end of the table they were actually testing their spoons out with droppers of water. So this is an activity that we could do with large audiences over a small period of time. And then the other two pictures actually show some demos that we do with students when we have them for a period of time. In fact, the upper right one is actually a grad student actually talking to a group of students about the forces that causes things to come together. And so that's a demo of our floating self-assembly. The bottom picture actually shows a discussion of the research that's going on in new generation solar cells. And so you'll notice that there's an example of the solar cell sitting there on the table. But then she's actually having the students make a thin film. And so it really depends on the type of audience that you're trying to do the demo to. We actually have a demo guidebook on our website, on our NNIM website. It actually has the common demos that we generally do when we have groups here at Tech. You'll notice that it has a variety of materials that you will need for the demo, but it also has suggestions on how to actually do the demo. So we actually have that demo guide on our website. Another great place to get demos is the NISNet website, which is also on your resource sheet. Another great way to do an introduction to nanoscale science is through games. This is a website that is nanomission.org, but if you look at the objective, this objective says that most young people think of nanotechnology as a futuristic technology. And they don't understand that they're already being impacted by nanotechnology in the world around them. But the other great thing I like about this game setup is this game was created with the understanding that we need to introduce students to nanotechnology, but they aimed it at the gaming generation. And I think a lot of us can agree that there's students know a lot about gaming out there. And so this is a way that you can incorporate their love of gaming with their learning of nanoscale science. So games are another great way to introduce students to nanotechnology. And the last resource that I want to spend time talking about today is even something as simple as trading cards. Here's an example of trading cards that comes from Rice University. They're at NanoKids website. And this is a set of trading cards that teaches students about products of nanotechnology, careers of nanotechnology, what kind of education you would need for those careers, and even tools of nanotechnology. So sometimes something as simple as just trading cards is a way that we can have our students learn something about nanoscale science.
Well, thank you, Joyce. Let's take a pause here for a moment for a couple of questions. Let me start with one. It has to do with levels. I mean, there's several questions in the chat window about the levels. So the games you were just talking about in the last couple of slides, what levels are those targeted toward? Are they 11, 12s? Are they 7, 8s? What do you think?
You really have to go to the resource because there's actually games out there that are targeted for middle school and high school. I would say the majority are those levels. But even if you check, for example, Rice University's NanoKids, there are actually websites out there that are actually geared for the younger students that are out there. So there's some of both out there.
Okay, good. So I think you're right. Obviously, it depends specifically on the resource. I did notice that one of our participants said that she used that Big Ideas book as an extra unit in her 6th grade. That impressed me. I thought that was pretty cool.
That's great. I mean, that's a great resource because it has a lot of guidance for teachers to use.
You know, one other question, this one's a little more specific, but the participant wonders if there's some upper level physics activities. In particular, I think he or she wants to know about, you know, is there something that might be associated with this concept of surface plasmon resonance? That's a harder concept for students to get. Are you aware of anything in that area? I'm not.
I think we would have to think about that a little bit, because there's a lot of things that are being developed, and I don't know how much of that is online. So if that's a person that can specifically send me or email me that question, we might can track down something.
Oh, good. I know we'll have your email at the end. Another set of questions comes about on the super hydrophobic materials, you know, the magic sands and so on. They seem to be just the thing that engages students. Don't you think? Many people have commented on that in the chat window, and I've seen that work too here in Arizona. What's the big attraction of this magic sand stuff?
Besides that kids love it. In fact,
well, yeah, that too.
The picture that I showed of us doing is that science. We do it all the time, but that particular night we did 1,500 plastic spoons. So there's a interest in it. But I think the big part of that is it's a way for kids to first see hydrophobic and hydrophilic, and then you can move the kids into where are hydrophobic materials, for example, in nature, and do things with types of leaves like, you know, lotus leaves and nasturtiums and, you know, all the hydrophobic materials out there in nature, and then move them over to how we've actually copied that and made consumer products like, you know, super hydrophobic coatings and building materials and clothes that cause, you know, so there's a lot of ways that you can take that interest and actually move the kids forward.
Well, that's cool. We're noticing that in the chat window that NanoLink, that's one of the ATE centers, offers hydrophobic activity, and they'll send the magic sand to you for free. So that obviates the need for you to find it on Amazon. So that's pretty cool. Boy, I just got this. That's a good thing I got out of this webinar today, Joyce. I'm going to write to NanoLink and get some from them. Joyce, we're perfectly on time here. Why don't we'll have another break for questions coming up. Why don't you go ahead and take us forward?
Okay, and again, let's make sure that we understand that if you have some great resources out there, we would love to add it to the list so that we can get them out to all the participants. I want to start off by talking about what if you, instead of just introducing nanoscale science to your students, you actually want to connect it to something that you cover in your curriculum. So one of the things I want to start off talking about is examples of K through 5. Here's a lesson that we do that's called the right tool for the job. Now, the whole purpose of this lesson being written was this thought that we're trying to encourage students to become engineers, but yet in the elementary grades, we don't really let them play around with tools. You know, we let them use measuring devices. We might have a out there in front of them, but other than that, students don't really play around with tools. So the big connection to nanoscale science is we know what we know about nanoscale science because of the tools that have been developed. So tools is a big thing in the area of nanoscale science. So here is a lesson based on this book, Manny's Book of Tools, because again, another thing that elementary teachers have come back and told us is that sometimes they have to get their science in through their math and their language arts. And so this lesson was actually written around this book. The book actually, to do this lesson, this slide actually shows some of the materials that we actually use to do this lesson. We actually take out to the classrooms boxes, you know, toolboxes. And one of the things that you'll notice in this lower left part of the slide is some examples of the tools that are in there, because now they actually make tools that are called little chubs. They're actually real tools, but they're actually small sizes which work great with kids when you take them out to the classroom. And so this lesson actually asks the kids to understand that there are tools that help us to see, tools that help us to measure, and tools that help us build and repair. And then this slide actually shows some of the classrooms that we've actually done this lesson with. You'll notice over here, this is a group of second graders who are actually in the center, because these lessons can either be teacher led, or they can actually be set up as learning centers. And so this is actually students who are in the Seeing Learning Center. And so these are students who have a variety of things that they are using in the center, all the way from USB scopes to microscopes to hand lenses. And of course this picture shows some students with the diffraction glasses on. And so they really, out of all the things that are in the Seeing Center, usually the students enjoy the 3D glasses and the diffraction glasses the best. And here's an example of the center that has to do with measuring. And this is a group of kindergarten teachers, kindergarten students that are actually learning about how to measure the ingredients for homemade Play-Doh. They actually make homemade Play-Doh in this center by using the measuring instruments that are in there. And then this is the building center, and they're actually using tools to actually build some of the Lowe's Saturday kits that they use with students. We've actually had Lowe's to donate several times kits that we can actually take out to schools to use. And then the bottom picture actually shows the lesson actually begins by having the students actually sort tool pictures into these three types of tools. So this is a lesson that actually helps them to build some skills on actually how to use tools. Here's an example of another lesson. Again, sometimes going through math to actually get to some science learning. This is a book that's How Much is a Million? And the lesson that was written around this book is sometimes we need large numbers to describe small things. Here's the reality. We're actually trying to get students in middle school and high school to understand what 1 out of a billion is, or what a nano is, when students don't really have a good idea of what a million or a billion of something would actually look like. And that's the whole purpose behind this book. He's written this book with many examples of what a million of something would actually look like. For example, if you were to put a million stars on a page, what would that actually look like? And so this lesson actually uses that idea to actually help students talk about this whole idea of what 1 out of a billion would look like. So here are some examples of some of the things that we use when we actually do this activity with students. You'll notice this bucket over here. Remember I said that these lessons can either be teacher-led or you can actually have them as learning centers. This is actually the bucket that we have all these materials in that we take out to work with students. And here are some of the other materials. I'm going to come back and talk about this one in just a minute, so I'm going to flip back and forth between these slides, because these are the types of things that we actually, the parts that we do with this lesson. We first taught the students about what a million of something would look like, and we use this container here, which is called a Becker bottle. And a Becker bottle, of course, is a container that has a million little beads in it. There are two different types you can get. One is a container that has all yellow beads, but one black bead. I kind of like this version of the Becker bottle because it has a lot of different colors, but the different number of beads vary by powers of 10. So for example, there's 10,000 of one color, there's 1,000 of another color, there's 100 of a color, 10 of a color. And when you start getting into 100 of a color and 10 of a color, you begin to see how difficult it is to actually find those colors. Another thing that we do with this activity is we actually give the students, and that's the reason I wanted to go back a slide, we actually give them a little case that has 10 beads in it, and we ask them to measure the length of those 10 beads. And then after they do that, we ask them, did you line up 1 million of these beads in your classroom? And so that's the reason you'll notice that there is a measuring tape in this learning center, because then the students would measure their classroom, and then they would decide whether there is enough room in that classroom to actually line up 1 million beads. And students that we work with on this lesson are almost always surprised, not only that they can't line up 1 million beads in the classroom, but that it would actually take over 1,000 usually classrooms to line up 1 million beads. So that's a way for them to actually begin to see how much 1 million would actually look like. Another thing that we use with this lesson is we then take that idea of what 1 million of something looks like, and we talk to the students about what would a solid, for example, look like if we were to open it up and look at the particles that make it up. So we don't necessarily talk to them at whatever age that we're doing in elementary about atoms and molecules, but we say if you just looked at the particles that make up a solid, for example, what would they look like? And so that's what these are. These are our structure of matter cases. This is the solid one, the liquid, and the gas structure. And so from that point, we ask the students to think about how small those particles would actually be. So the last part of this lesson, which we usually don't do, we only use this last extension part with upper elementary, 5th grade, for example, and middle school. We actually ask the students, if you knew how big one of these particles would be, how many of those could you get to line up across a centimeter? And so we give them some information about the cesium atom, and we ask them to actually calculate how many cesium atoms could actually line up across the centimeter. And when they actually get through with it, it's over 14 million. And see, with a Becker bottle in front of them, that's a way that they can see. That's 14 of those containers full of atoms that would actually be lined up side by side across the centimeter. It's a way for them to begin to understand how small the matter is that actually makes up solids, liquids, and gases. So what about some examples for 6 through 12? One of the things is we're trying to find, we want to connect to something that's already in curriculum. So a lot of times in curriculum, magnetism is actually covered. So this is a lesson that you can take and actually begin with what students already know about magnetism, and then help them to understand the differences between the macro sizes of particles that they're usually working with and the colloidal mixture that we call ferrofluids. And so this is actually an activity that we use 4 different containers with. One container just has iron filings. One container has iron filings and water. One container just has ferrofluid, and this one has ferrofluid and a penny. And so ferrofluid is it's like magic sand. Kids love ferrofluid, but it's a great way for them to connect all the way from understanding mixtures like colloids all the way to connecting what they know about magnetism. And so we've got a short video that I wanted to show you that you can actually show your students about ferrofluids. There's lots of videos out there. If you Google ferrofluid videos, you find a lot of them. A lot of them have to do with art projects that are made with ferrofluid, but this one is actually how ferrofluid actually works.
Now, Joyce, I'm going to go ahead and launch this video. It'll take just a moment here. And Joyce, you won't be hearing anything since the video is played individually at each one's computer. And participants, you may have to start the video. It depends on your system. If you see a forward button when your video appears, just go ahead and click on it. So I think this is right about 2 minutes long, right? So we're going to go ahead and we're going to launch this right now. Hopefully it's going to go here just a moment. So Joyce, we're back now. I couldn't help noticing at about 1 minute and 10 seconds in, that was very impressive where he lowers that sort of outsized Petri dish on top of the magnet and the fluid, comes together. That was pretty cool. And as you mentioned, there's in the right-hand side of that YouTube, there's dozens of ferrofluid demonstrations out there as well.
There's lots of resources out there that teachers can use. I think I like this one because it's a great description of how ferrofluid works. And he points out that it has a strong connection to, there's chemistry and physics to explain how ferrofluid works. But as I watch a video like that, I also think about all the topics in a biological sense that you could actually connect on how there are processes in the biological environment that actually work on that same way that the surfactant works. And so there are some great ways to actually utilize those types of things in the curriculum. But ferrofluid is one of those things that that you can take what students already know and actually introduce them to a material that most students are fascinated by. Here's another resource. This is actually, again, a resource from NanoSense. This is a unit that's called Clean Energy. This unit actually, again, is a longer unit. The great thing about it, again, is that you can, if you don't have time to do the whole unit, that you can pick parts of the unit possibly to do. But this is actually, in a lot of state standards, energy is one of those things that students learn about. This one has a great introduction to it. There's an introductory PowerPoint that's with it, and part of the discussion at the very beginning of this PowerPoint is having the students to decide what the top 10 global problems will be over the next 50 years. And that's a great topic for students to actually think about. And when we've had students to actually stop and do this, it's kind of interesting to see what kind of topics that they actually come up with. And so then that becomes part of this introductory PowerPoint. And so this is actually an activity, this is actually a unit where students look at the clean energy resources that are out there, and solar energy is highlighted, and it actually has the students compare traditional silicon solar cells with nanocrystalline solar cells. And the students will actually have an opportunity, if you do the activities with the unit, to actually create a nanocrystalline solar cell from berry juice. The other thing that I like about this unit is it has a great simulation for solar cells. A lot of times students don't really understand what happens when that energy from the sun actually hits that solar cell. So this simulation not only shows what happens in a traditional silicon solar cell, but also it has a simulation for the nanocrystalline solar cell as well. Another resource that's out there is a lesson that's on identifying DNA. A lot of schools have gel electrophoresis chambers, but some schools don't. So this is actually an activity that actually is a way for schools or teachers who don't have those type of chambers to actually show students how it is possible for DNA to be separated based on mass and also charge. And so this is an activity that uses a traveling soap dish to actually use as the chamber. And the students will actually separate out, instead of DNA, they will actually separate out food coloring. And so it's an opportunity for you to talk about how DNA falls in the nano world. By definition, a nanostructure is between 1 to 100 nanometers in at least one dimension. So DNA is between 1 to 2 nanometers in width, so that identifies it as a nanostructure. So this is an activity, I want to show you some teachers actually doing this activity, because teachers are great at coming up with ways to change or improve or how they're going to actually use an activity. And the reason I want to show you teachers actually doing this activity is because I've had a couple of teachers who actually have gel electrophoresis chambers tell me that they do this activity to start off with their students, because one of the problems with sometimes that activity is actually having them fill the wells. And so this is a way that students can actually practice pipetting into those wells, and you'll notice the teachers actually pipetting in the food coloring into these wells. It's also a way for them to actually troubleshoot sometimes with students on getting these chambers set up correctly. And so this is a great way to do it. This activity, by the way, and I'll click back to the original slide, is actually a forensic science activity. And that's a great way to get students interested in the topic because, of course, with all the CSI programs and all on television, kids are interested in forensic science. Here's a lesson that was actually created to teach kids about acids and bases. So it was actually developed as a chemistry lesson to have students learn about pH and strong and weak acids and strong and weak bases. So it's a great activity that creates a whole knowledge base for students on acids and bases. But it also has students think about what they know about encapsulation and actually connecting that knowledge of encapsulation with what's going on in the research world. There's actually an extension of this lesson that I often use with students. It actually has to do with biology, because in biology we often test organic materials like a complex sugar, like a polysaccharide, and we do that using iodide. So this is actually an activity that I do where students actually encapsulate either starch or iodine. So you'll notice that there's a microplate up here in this picture. The first well in the microplate, this one right here, actually has calcium chloride in it. This actually has starch solution in it. And then this one actually has iodine solution in it. So you have this microplate that has these three solutions in it. And what you put into this calcium chloride is alginate, sodium alginate, which actually is a polymer that has a negative carboxyl group on the end. And so when it's put down into calcium chloride solution, because calcium has ionized and it has a positive 2 charge, it begins to attach strands of this polymer together. And so whatever this polymer is in actually is trapped inside these strands. So in some of these beads, you mix the sodium alginate with starch solution, and in some of them you mix them with iodine solution. So when it's all over with, the students will actually encapsulate iodine or starch in beads. Here's an example of iodine beads being placed into starch water. And you'll notice that the water starts to become purple or dark because there's a positive reaction for the presence of that complex sugar or that starch. And so what students are asked to think through as they progress through the lesson, here's an example of starch beads being put into iodine water. They are asked to think about, where is that reaction taking place at? Is it taking place on the inside of the bead? For example, right here, the dark is on the inside. Or is it taking place on the outside? So that students can begin to understand that even though this has iodine in it and this has starch, both of those materials won't cross that membrane. Iodine is small enough that it can cross the membrane, but starch is too big of a molecule to cross over. So it's a great way in biology classes for all of those teachers who have been doing dialysis tubing, those type of things. The same thing can be done to actually address those standards that have to do with facilitated diffusion, osmosis. It's a great way to actually do that. But the great thing is then you can have a discussion about how encapsulated materials such as these are actually being used in the research world to possibly encapsulate medicine and also to encapsulate fluorescent materials that we can actually use to identify diseased materials. So here's an example of actually teachers actually doing this activity. And you'll notice here how they're getting a reaction for those materials to actually show up. So this is a great way that you can take a traditional activity that you've always done to meet a standard, and actually use an activity that actually shows how you can incorporate it to cutting-edge research. This is a great lesson that's actually called Move a Wall. This is actually a lesson that has students understand that you don't necessarily have to see large motions or movements to actually be able to calculate how much they move. This lesson actually starts by having a student push on the wall. And often when I'm in a classroom to do this lesson with students, I try to look around and find somebody that possibly is in a football jersey, but possibly a football player. So you want somebody who can really push on a wall. The thing that you want to make sure of is that they push on a good sturdy outside wall. And after they push on the wall, then you ask the students, did the wall move? Some students will say yes, some students will say no, but then your next question to students is, well, how do you know that it did or did not move? And so then you begin to talk to the students about what evidence they have. And so then this is actually a lesson that actually shows them how you can be provided some evidence to actually show whether the wall moves or not. So this lesson actually has a great set of visuals with it. It actually shows you exactly how to set this activity up. It also actually shows you how you can use a large demo piece before the students actually do this activity. In fact, this is the wall. This board represents the wall. This actually represents the rod, the metal rod, that you actually, here's an example of a picture of the metal rod, that you actually stick to the wall using carpet tape. Now you use carpet tape because carpet tape is really, really sticky, and when you ram the rod up to the wall, it will stick to the wall. So what do these dowel rods represent? They actually represent T-pins. This metal rod actually sits on T-pins, and there's a little mirror that's stuck to the end of one of these T-pins. So if you look at the diagram of how this activity is actually set up, here's the rod that is, here's the wall that's pushed on. Here's the metal rod that's actually pushed into the wall, and the two T-pins. Now the other part of what you need for this activity is actually a laser that you can bounce off, the laser light to bounce off of this little mirror. I use construction. This activity calls for construction layers, and the reason for that is if you're doing this with a variety of classrooms, you never know what height the tables are. And so the legs, the tripod to these laser levels can be raised and lowered. But you need a laser light that actually bounces off of this mirror. And then the students mark the beginning point of where the laser light is. And then once the wall is pushed on, it pulls the rod, which rotates the mirror, which actually changes the place where the laser point actually hits the opposite wall. And so then the students actually use their trig to actually figure out how much this wall actually moves. Now, I'm going to show you some pictures of teachers actually doing this activity, but I want to also tell you some things that I've learned in doing this activity with students. The first thing is, often when you're doing it with classrooms of students, often the classrooms have lots of students. And so sometimes you have to set multiple groups up on the same wall. So just like these teachers are actually taking turns pushing on this wall, you have to make sure that your groups know to not all push at the same time. The other thing that I want you to understand about this activity is when I've gone out and done this activity, sometimes I don't know where teachers' classrooms are at. So I have taken this material out to classrooms that are not on the bottom floor. And so I'm talking upper levels of a school building. And you can still do the activity on those upper levels. The only thing that I say is an extra lesson that students learn when you do that is how flexible the floors are, because you'll begin to notice how much vibrations that you actually get from that activity when you do it in classrooms that are on upper floors. So the best thing to do is to actually do it in a classroom that's on the bottom floor. Here's actually an activity that you can use to either develop students' knowledge of mixtures or actually to see how much they actually know about mixtures. And since over 80% of the material around us in the world around us is mixtures, mixtures is one of those things that students should have a good understanding of. This is actually a set of mixture cards. So it's cards that have a different mixture on them. And so what this lesson actually does is it actually has the students work through a sheet where the students are separating out their cards in a variety of different ways. Part of the lesson actually has the students put their groups on sheets that they actually put up on the wall so that they can compare their characteristics and groups with each other. It's a great way for students to actually teach each other. In fact, when you start this lesson off and you just ask them to just put the cards in any groups that they want, the one that most of the time is actually picked is students will actually separate them based on solids, liquids, and gases. The interesting thing about that is even though there may be 5 groups that have divided their cards, solids, liquids, and gases, it's very rare for their groups to all have the same cards in it. And so that gives the kids an opportunity to talk to each other about why did you put this mixture in this group. But by the time they get through with this lesson, they've divided the cards up into homogeneous mixtures, colloids, and the other homogeneous mixtures. That's what the lesson has them to separate the cards in. And so where's the nano connection? A colloid is a colloid because the particle size is between 1 to 100. That's the reason that the particles don't settle out, but that's also the reason that they're big enough to scatter light. And so when you've done that lesson in a physical science or a chemistry class, talking to kids about the differences between suspensions and colloids and solutions, you've done a nano lesson because those characteristics sometimes are based on the size of the particles. So here's an example of teachers actually doing, I've done this lesson many times with students. The problem sometimes with me doing activities with students and pictures is I'm working with the students, and so I can't take pictures and work with students at the same time. But here's groups of teachers who are actually doing this activity. You'll notice here they're putting their groups on the wall so that they can actually compare. The funny thing about teachers doing this activity is that the mixtures that are on these cards are kind of challenging, and sometimes you see teachers getting out their smartphones and their iPads to actually look up and see what some of these mixtures, how you would actually classify some of these mixtures. So I've actually had workshops of teachers where teachers have come back and said, you know, by doing this kind of card sorting, I actually have a better understanding of how to describe and work with mixtures with my students. And so this is an activity that actually just uses a set of cards. I like activities that are cheap and easy for teachers to actually use. So oftentimes you see me using activities with cards.
Joyce, I just want to interrupt for just a second. I know you're heading into, this is about our last example, I think. Your timing is really good. We've got about 10 minutes to go, so thanks.
Okay, thanks. This is actually, in the past couple of years, I've had a lot of teachers that have come to me and said that their schools are getting 3D printers, and I think that's fantastic. But this is actually a lesson, maybe you're a teacher that doesn't have a way to help your students to see that we can make very complex things without actually touching those objects. This is actually an activity where you use a polymer, and you can actually, I don't know if you can see, but these are actually nickels and dimes and quarters of these objects. This is the Lincoln Memorial and chess pieces. This is a piano. But these are actually 3D structures that were made from a polymer that was actually activated from the UV radiation from an LCD projector. So you use an LCD projector to do this. I don't see the football goal, but when we do this with our Exploring Nanotechnology camps, the popular structure to make was a little tiny basketball goal. But this actually activity has videos that actually show you how to set these activities up. It does use some chemicals that have to be ordered, but the great thing is once you make these materials, them together, you can make several structures from that one set of materials. And so the materials are actually made by using a PowerPoint program. It's like slicing through the 3D object. Every slide is a piece or a layer of that object. And you'll notice that some of the slides are red and some of them are white. That's because the red color will not activate the polymer, but the white will actually cause the white light from the LCD projector to have enough UV radiation to solidify that polymer or to react with that polymer. And so here's an example of a 4-slide PowerPoint that I did to create a little 3D structure that I use in teacher workshops so that teachers can actually take it with them when they leave. This is an example of how you can use change phase activity. A lot of teachers do change phase, energy of transition. This is where you can use something that's not traditional, a traditional material like the melting of a piece of ice, and actually use a material called nitinol, which is a smart memory alloy. The thing that's unique about nitinol is it has 2 crystalline arrangements for a solid phase. And I think there's lots of us out there that never talk to our students about the possibility that substances are out there that may have more than one crystalline arrangement, for example, in a solid phase. And so that's an example of nitinol. So this was an example of a teacher who actually had her students calculate the transition temperature at which this nitinol actually goes back to its original shape. The other thing that she actually did with her students is she actually challenged them after they got through with these calculations to actually come up with a way that they could actually use nitinol. And she had groups that designed things all the way from how you could untangle your earbud cords. And so she had students that actually took nitinol, put on the earbud cords, because everybody sticks them in their backpacks and their pockets, and when they pull them out, they're all tangled up. And then they connected the nitinol to batteries, and of course, it straightened out and untangled the cord. So she had some great examples of how the students actually designed with nitinol. I actually want to say a little bit about NNIN. We are a network of 14 research universities. Georgia Tech just happens to be one of them. And we're funded by the National Science Foundation. And one of our missions is to actually do outreach to pre-K, K-12, grad students, undergrads, professionals, and even the general public. So we have a website. This is our website here with some great resources that you can download, as well as this resource right here. This is actually an online magazine. The target audience for this magazine is 5th through 8th, but we found out that it works great for our high school students, because if high school students don't know anything about nanoscale science, this is a great place for them to get a little information. The other thing that I want to mention to teachers is if you go to the info at Nanos and tell them you are a teacher, they will actually send you classroom packets of the Nanos free of charge. So sometimes teachers might not have the resources for a lot of students to get online. They'll actually send you paper copies of this magazine. And of course, I want to say a little bit about the NAC. This is the NAC website, nanoforme.org. This, again, is a great place for you, even though they do a lot of work with trying to help technical and community colleges develop manufacturing courses or programs. They have some great resources for our K-12 teachers. And again, I want to say a little bit about the resource list. You'll get a list of books, and there are some for K all the way through 12, recommended for those ages, as well as a separate document which is internet and multimedia resources. But these are only a beginning. I don't want anyone on the webinar to think that this is a complete list. This is just a list that I hope will be a beginning of a whole catalog of resources that are actually out there, because all of us are going to have to work together to help move our forward in this area of nanoscale science and engineering. And part of that is helping all of us find resources out there that we can actually use. So kind of to conclude, again, hopefully I've helped to provide you with some reasons for actually sharing nanoscale science with your students, and to show you that there are some big ideas in nanoscales out there to help guide teachers. and how they actually connect to the curriculum, and hopefully to show you just the tip of the iceberg on some resources and how you can actually use those out there with your students to introduce students to nanoscale science, and also to connect them to the curriculum that you already teach. So Mike, that's...
Well, thank you, Joyce. Let's take a question, and then I want to ask our participants help with a very brief survey. But let's start with this one, and we have Bob Ehrman on the line too. He might be willing to chime in. The question is, are colleges now offering nanoscience degree specializations? And I think what the question means is, can you, for example, get a chemistry associate's degree with a nanoscience specialization? I think that's the sense of the question. What do you think, Joyce? And let's hear from you first, and then ask Bob to chime in.
I know Bob has a better take on this question than I do, but I do know that there are. It really depends on the institutions. So, for example, some institutions will just give a certification if you've taken a variety of nano-based courses, all the way to their colleges and universities that are offering types of degrees. But Bob can answer that much better than I.
Thanks, Joyce. Oh yeah, thanks, Joyce and Mike. Yeah, absolutely. That's actually our role, is to enable nanotechnology education across the country, and at community and technical colleges, as well as universities who are in partnership with community and technical colleges. And there are straight baccalaureate degrees out there, like the College of Nanoscale Science at Albany is one to begin with, and they have an awesome program there. But there are also workforce development programs all across the country. There are about 25 of them right now in the country. If you go to nanoforme.org, I can't go through them right now. Pennsylvania has partnerships with 52 different degree programs that specialize in just what you said, Mike. A chemistry associate degree with a specialization in nanotechnology, which consists of 6 courses that make these students work ready. And there's pockets of this all across the country in programs that are in nanoscience and nanotechnology, and there are different flavors all across. I encourage you to go to nanoforme.org, the front page, and you'll be able to click on your state and figure out what's going on in your state. And I apologize if people are online or know of others that are out there that I'm not aware of, or that we haven't put on our map. And please let me know if we've shortchanged anyone, if there's more out there to be had.
Well, thanks, Bob. We've just had a great interaction in the chat window today, and if you look at the last several chats, you'll see people that are indicating the programs they know. For example, the one at San Bernardino Community College, as well as the one at the College for Nanoscale Science and Engineering up in the Albany area, plus some others. So it's really good, Bob. I think we want to mine this chat window later and help make connections of our own there. So I think it's really good.
I learned some awesome stuff through that chat window, Mike. There's some really great stuff. I mean, if you would have done this webinar 5 years ago, it would have been a very different chat window. So I'm really, really super excited about it, about what's going on.
I agree. Folks online, we've asked you to help us pay the bills. That's my little joke. But if you'll take just a moment to click on those radio buttons and maybe type in a suggestion into the survey, it should take you about 60 to 90 seconds to do so. That helps us demonstrate the impact that this webinar series has to our funders, the National Science Foundation. So we appreciate it very much. Joyce, I appreciate your comments of explaining why we ask folks to sign in. We do want to be able to demonstrate, as you mentioned then, people actually using the resources that we provide. That just helps us do more. Joyce, one other question for you. By the way, your timing was so perfect today. We're right at the concluding moment of our webinar. I saw several things which struck me in the chat window. A lot of them had to do with integrating these nano activities into other things. I'll give you an example. One person said they want to combine this with an astro lecture, astrophysics, where they think they're talking about scaling and microscopy. I couldn't help relating on my own sense as I look at my chemistry. I was thinking about when I do acids and bases. I could do that encapsulated one where I talk about the acid-base properties, but then bring in encapsulation and nano stuff right at the same time. Several chemistry folks in the chat window talking about using these things. We really see the potential here, Joyce. I think you see it too. Do you want to make a comment there as we get ready to wrap this up?
Well, that's the whole value in doing something like a webinar where you have a whole variety of people online, because I think each teacher, each person, even if you're not a teacher, you're coming to nanoscale science with your own perspective and your own strengths and knowledge. And so a lot of times when I give out an idea, I don't want teachers to go and use that exact idea. I want you to think about the students that you have and how can you utilize that idea. And then hopefully, my hope is that people begin to share how they've incorporated these things so that we can pass them on to other teachers. Because the reality is there's lots and lots and lots of things out there about nanoscale science. How can we help teachers who don't have time to go out there and search these things down? How can we help these teachers be able to locate these points of discussions in their curriculum and have an idea of how to actually address them? So that's this whole idea of us all working together.
Thank you, Joyce. You know what, folks online, I'm getting ready to close the survey. So if you're rapidly typing a tome, whatever that is, into the question box, hurry up, because I'm just getting ready to close it. I'll count down from 5, and then we'll wrap up for today. So here we go, closing the survey in 5, 4, 3, 2, 1. And thank you again for participating there. You know, as we think about this webinar today, whether you joined us live or watching in person, maybe you're seeing this on a replay, you can participate in our questionnaire that we just had as well. All of us will get access to this recording, the slides, and a special handout that Joyce has prepared that lists all of these resources. Thank you again, Joyce, for doing that. Some of you might want a certificate saying that, hey, I attended this 1.5-hour webinar and would like a certificate. Please email Sue Barger. You see her name there, sbarger@engr.psu.edu. So go ahead and shoot an email to Sue and you'll get a certificate. Coming up, Bob, there's some pretty exciting things coming up for the NAC network. The next webinar talks about a specific RET, research experience for teachers, Joyce mentioned that today, and how those translate to activities for the high school classroom. That's on March 28th. On April 7th, I know you're hosting a workshop, Bob, your first level course resources workshop. Another webinar on April 25th on how to engage industry partners for your nano program. This is a busy spring you've got going here, Bob. And then another workshop in May, hands-on introduction to nanotechnology for educators. Bob, are there fees for those workshops?
No, there are not. There is an application criteria for the workshops, and unfortunately space is limited. So if you are interested, again, that nanoforme.org website is the place to go, and go to educators, and actually you can get it from the front page, but you also get it from educators /workshops at the same place you can get webinars there. So you can go there, and there's an application form that you can fill out, and then we do select from the pool of applicants that do come through. But those who are selected do get to come courtesy of the National Science Foundation Advanced Technological Education Program. So one thing, Mike, while I have the floor here, I really want to thank Joyce, and for those of you who don't know her, and I feared a lot of people did, she's a fabulous resource. I've known her for years now, and I'm really happy that she made the time to, and a lot of time she's put into this, and I really appreciate all the efforts that she's made for us, for the NAC network, and for the educators of the country.
I totally agree, and thank you, Joyce. I bet you your voice is exhausted. We went through so much material today, but it was perfect. It was really good, so thank you again. Now, folks,
thank you for asking, and
yes.
I really do hope can find a group of all of us to work together to actually increase the amount of resources that we have out there.
That's a great idea. That was one of the suggestions. By the way, folks, the webinar is officially over, and we're just wrapping up here. We're still live. Joyce, one of the people on the chat window said, is there a forum? Is there a place to do this? And I think there is, Bob, in a way. The NAT network is providing more and more of this forum for exchange of resources. So hopefully we can build on that. Now, one more thing. A copy of the presentation, you will, by registering for this webinar, and by Monday at noon Eastern, you'll have in your email a link to the copy of the presentation. So no worries there. You know, Bob, they can also see all of the prior webinars on nano4me.org. You have under your webinar tab there, you've got them all. So,
yes,
Bob, you put your last word. Go ahead.
Yeah, we have over 20 webinars there. If you're interested and they're on topics, if you want to know a little about what's going on in nano in food or nano in medicine or nano in energy, there's great webinars there for you to look at in our archives. If you want to go back to this webinar, they're there for your consumption at any time. Or please let your colleagues know about them. Hopefully they'll be helpful to you and giving us a more nano-literate population, getting those numbers up that Joyce showed in the presentation today.
Nano-literacy, I like that. Yeah, go ahead, Joyce.
That Mike is the link on Monday also where they'll link out to the resource list?
We're actually going to send that resource list to them as a PDF, and there'll be a link showing it. Yes, so they'll get that too on Monday as well. It's all ready to go. So that'll be good.
Okay.
So that officially concludes, Bob and Joyce. I'm going to ask you to stay on the line for just a moment. I'm going to close the sound system here so the attendees won't be listening to us anymore. Bob, there's some follow-up for you in the chat window. People I want to do some things with you, so I'll send you a copy of that chat as well. So this officially concludes. Goodbye, everyone.